So tension in the surface, right? You understand? Surface tension, tension in the surface. You have had this experience. You have you all seen those tense-like things? Like where you can see kind of a, can you all see the screen? Yeah, right? So then think of this like a tent. Think of a situation where the cat is moving in this. Have you all seen that this stretches?
Yes,
Stretching,
yes.
right? Yeah, stretching when there's an object, it stretches. But this surface wants to come back to its position. No? There's some tension there. Can you see? There's some tension. For this to be balanced, of course, forms like social doctrine so that its weight is balanced. No? Right? So you should understand then this is a surface phenomenon. Tension in the surface.
So it
Okay?
sounds a
You
lot
get
like
some idea.
elastic stuff.
Yeah, it has that elastic nature in the surface. Okay? That elastic nature is there in the surface tension. So when you talk about tension, we have that elastic idea, stretching, Okay? If you have a wire, when you stretch the wire, it's going to be under tension, right? You have that perception. Okay? Right. So now just have that holistic idea about what surface tension. Surface tension is. What is surface tension? So surface tension is the phenomenon in which the surface of a liquid acts as an elastic film. We just understood that, right? So it's the phenomenon in which the surface of a liquid acts as an elastic film. And the attractive forces between homogeneous molecules, you all should know this idea. The attractive forces between homogeneous molecules. What are homogeneous molecules? The molecules of the same type, right? So the attractive forces between homogeneous molecules is called what? Cohesion, while the attraction between heterogeneous molecules is called adhesion. Attraction between heterogeneous molecules is called adhesion, right? So the attraction between water molecules is cohesion, but the attraction between water molecules and what? The xylem vessel walls is what? Adhesion. Remember, you've learned these things. So the cohesion allows the water molecules to stay together, and at the same time, adhesion allows what? The water molecules to adhere to the surface of what? The xylem vessel. Therefore, they can move as a continuous column up against gravity, and they're going in the xylem vessels upwards, right? Because of the transpiration pull, they can go upwards, but they go upwards against gravitational pull because they are this continuous cylinder, right? In this continuous cylinder, the liquid is attached to what? The xylem vessel walls. You've learned this, right? Xylem vessels, for the math students, those xylem vessels are those vessels which carry water and minerals in the plants, right? So, okay, I hope you all understood that particular section. So, now we've
Yes,
got to get into what is the molecular behavior of the free surface of a liquid. How do the molecules behave? And what does this behavior pronounce? What does this behavior bring about, right? That is our central question here. What molecular behavior brings about this phenomena of surface tension? Where in the world is this coming out from, right? So we're going to see that now. You see, when you think, summarize what I just discussed, if you observe a molecule like A, it's experiencing what? Forces all around like that, right? Forces all around like that. So you can see the resultant force acting on a molecule like A0. Three-dimensionally, these forces are acting and they're cancelling off three-dimensionally. But if you draw a molecule like B, it is also experiencing the same thing, but it's very close to what? The free surface of the liquid. It's very close to the free surface of the liquid. Very close to what? The free surface of the liquid. That is true. It's very close to the free surface of the liquid. But then again, still, it's not experiencing a net force. It's not experiencing a resultant force. But now, if you think about a molecule like C, what can you say? You look at C, forces, some forces are cancelling off, but not all forces. Some interactions are missing here, right? Some vectors cancel off, but some vectors are not cancelling off. Therefore, the resultant vector is going to be acting downwards, right? So this cancels with this cancels with this, and so on. So, but those although those vectors are cancelling off, there is no one to cancel off this vector, for example, this vector acting downwards, for example, right? So then, if you think about another occasion like D, what can we say? You can see entire half of what? The sphere of influence. We say this particular sphere is what? The sphere of influence. One half of the sphere of influence is gone missing, right? One half of the sphere of influence is gone missing. The only thing that's happening there is what? There are some air molecules that can interact with water a little bit. So there's a small force, but that is negligible compared to what? The attraction that is acting downwards, right? So the sphere that we draw, I forgot to mention this earlier. The sphere that I draw is what? The sphere of influence. Sphere of influence. Okay. Now we're going to go deeper into this. The greatest distance at which the molecules can attract each other is called what? Molecular range. Greatest distance at which molecules can attract each other is called what? The molecular range. There's some kind of a distance, like 10 to the minus 7, some say 10 to the minus 9. So that kind of a distance is there. That is the minimum distance, right? That's the greatest distance at which the molecules can attract each other. Beyond that, if the distance is there, what will happen? If the distance is beyond what? The molecular range, will there be a substantial attraction? No. Is it understood? So the greatest distance at which the molecules can attract each other is called the molecular range, because beyond that distance, there won't be a substantial attraction.
So is
So
it
then,
is that attraction related to Coulomb's law?
yeah, Coulomb's law in one sense, because but there are complexities. What's your name again? I forgot your name. Minuka, right? Minuka. So Coulomb's law in the sense we can apply it, but not in the traditional sense, no? Because these interactions between water molecules, yeah, there are polarities, like if you think about a water molecule, there are what? Polarities, no? Delta H plus, delta minus. Of course, there are these temporary polarities that, help the water molecules to attract themselves. But it's not like a pure charge, no? You understand that, Minuka? It's not like a pure charge. But of course, there's some attraction. Then we have to do some corrections, of course, when you're applying these equations. Do you understand? That clear now?
So I have a
Okay, good. So the sphere drawn around the molecule, in which the molecule at its center and the molecular range as its radius is called what? The sphere of influence, or the sphere of molecular attraction. Beyond that, will there be an attraction? No. Right? So that's the molecular range in which there's an attraction. Okay. As seen in the diagram drawn above, the resultant force acting on liquid molecule A is 0. Now we can understand it's 0, right? We have gone through this, right? So the resultant forces acting, right? Let's make a small correction there. Resultant forces acting on molecules C and D are downwards. Is that clear? Right. Surface film is
Yes,
defined as the liquid layer that has a thickness equal to the distance of the molecular range of a molecule. What is the molecular range? This particular distance is what? The molecular range. That is going to be the surface tension. Sorry, surface film. Surface film is what? This molecular range. Because I'm thinking of that as a radius. Is that clear? The sphere drawn around the molecule, in which the molecule at its center and the molecular range as its radius. See, so we consider the molecular range as what? The radius. So this is the radius, right? If you think about it, this is the radius, no? That radius is called what? The molecular range, and that molecular range is what? The surface film. Is that all clear now?
Yeah, sir. That's clear.
Okay. All right.
Yes, sir.
Now, as there is a resultant force acting downwards on the molecules, work has to be done for the molecules to go to the free surface to overcome the attractive forces acting downwards on the liquid, right? Now see, there's a net force acting downwards. So if there's a resultant force acting downwards, is it easy for these water molecules to go up?
No.
Can they just go up? No, there's an external unbalanced force acting downwards. So that's not going to be easy for the water molecules to travel upwards. So therefore, what should happen? Work has to be done, right? Work has to be done so that these water molecules can go upwards. So if they have enough kinetic energy, they can overcome this repulsion and get upwards. No? Is that clear? So they can reach the surface film if they have enough kinetic energy, overcoming the repulsive forces acting downwards. Okay? Right. So that is understood. So therefore the work when these molecules reach, therefore the work done when these molecules reach the free surface is stored as what? Potential energy of the liquid molecules at the surface film. Do you understand that? They have done some work, right? They have done some work when they're coming upwards and they're going to be at this position. So now they've stored what? Potential energy. Okay? Right. So they have some energy now. And that energy also gives you an idea about surface tension, right? Do you all feel that in the same way that I do? They've done work. They've gone up to what? A particular level. That is the surface film. So they have gone up to the surface film, right? They've reached that particular level, overcoming all those repulsive forces acting downwards. So once they've come to that particular level, right, they are going to store now potential energy. And do you all feel in the same way that I feel that this is associated with that tension, that idea of tension? Do you all feel that? They have that energy now in that position and they're staying there with that energy. Do you all feel that?
Yeah, sir.
Have that perception, right? Yeah.
Okay.
So the system is more stable when its potential energy is at a minimum. Do you all understand that? It's more stable, right? When the potential energy of a system is minimum, system is stable. You all know that, right?
Yes.
So if it's at this position, when it comes to this position, it's more stable. An object. Right? So lower the potential energy, lower the potential energy, greater the stability of the system. Okay, and you all have to understand, if you go into deep thermodynamics, actually we can't only talk about the energy for stability, we have to also talk about entropy, but that's in high thermodynamics. Once you all get into universities, you all will learn that properly. But for now, at your level, just remember, low energy means what? High stability. Therefore, the film, therefore the film is more stable when it reduces the potential energy at the surface. Do you understand that? Right? The film is going to be more stable when it reduces the potential energy. So just imagine, it's like these water molecules are agitated, no? Yeah, they're coming there and they're staying there. It's like a struggle. I don't know, that's how I feel it, right? They have this potential energy and they're there, all right? But it's not a stable thing, is it? Right? It's not stable. There's a resultant force acting downwards and they eventually come there, and it's not easy to stay there. They're clear, right? So, but they have come to that position, so that's an unstable state, but they are there, right? So, but what does nature do? Nature will always try to what? Bring about stability in the presence of what? Instability. Is that clear? Okay. So, what will nature do then? What will nature do? It will try to bring the potential energy of the system down, right? So it's trying to bring the potential energy of the system down. It's trying to minimize the potential energy. How would it minimize the potential energy at the surface? If you can reduce the number of molecules in the surface film, then we are reducing what? The potential energy. The more molecules we have, the more energy we have, right, at the surface. So the less molecules we have at the surface, the less potential energy we have at the surface. Therefore, greater is going to be the stability of the system. Is that understood? Okay.
Yeah, sure.
Yes.
So now you have to understand, the free surface area has to reduce, right? Therefore, the overall free surface area has to reduce. The surface area of a liquid volume reduces when the liquid surface takes a spherical shape. This is a mathematical thing, a geometry that allows for what? A lower surface area of a particular liquid volume. You can do the math and see, right? It's a beautiful thing. So what happens is the liquid is trying to conform into what? A kind of a spherical shape, which what? Reduces the effective area and therefore stabilizes the system. Therefore, the liquid system tries to achieve what we call a spherical shape, or more or less a spherical shape. They're clear. This explains the reason as to why a stretched nature is exhibited by the surface film, right? Doesn't that in a sense explain why there's this stretched nature? Because it's trying to become spherical. When a flat thing is trying to become spherical, don't you feel that it's trying to get stretched in nature? Do you have that
Like a
perception?
balloon, sir.
Yeah, it's like a balloon. See, it's general. This is a perception. They're clear. Okay.
So it's
Right.
like
Isn't
not
this
exactly
beautiful?
becoming spherical, it's just like it's trying to be.
Yeah, I mean, they're trying their best to minimize the energy of the system, right? Or what? Coefficient of surface tension. Now, I think I already explained this on the boat. The force per unit length of a line drawn at the surface of a liquid. Force per unit length of a line drawn at the surface of a liquid. Right? We talked about this. We said, right, there is a particular free surface, right? A free surface like this, a particular free surface, right? And then if you draw a line like that, and if you mark all the forces towards one side, okay, so the resulting force then is acting like that. And if this length is L, of course, you know, but on both sides, this line is being balanced, right? The force is acting because it's stretched, it's acting from both sides. But you see, overall, the resultant force is going to be acting towards one specific direction. If you think only one side, if you think only about one side, then there's a resultant force acting in a specific direction. So this force F acting is equal to what? Surface tension into length L. We understood the force acting on a unit length is surface tension. Therefore, surface tension, overall force, this total force is acting on that particular line of length L is equal to what? Surface tension into length L. So this capital T is what? Surface tension. Or we also say coefficient of surface tension, right? F equals T into L. So F over L is equal to T, right? Very important. And of course, you all know the dimensions now. I don't think I have to explain those things, right? Dimensions of force and the 9 dimensions of length. Substitute them, then you can find out the dimensions of surface tension. And also, like, yeah, the basic thing is molecules are going to gain kinetic energy, right? The vigorous motion, no, like, see, more kinetic, the higher the temperature, greater the vibrational kinetic energy. The molecules are like agitated. They're trying to move apart, as Amaya said. It's trying to move apart, right? And then, is that what you said? So, yeah, because now
I said less
the
time.
molecules are trying to drive themselves apart. As you increase the temperature, the attractions are going to be less, no? The
So it's
attractions.
less
So,
tension.
yeah, so it's like
Okay.
there's There's weaker, what we call intermolecular attraction. Weaker intermolecular attraction. Inter means between. Molecular means molecule. So there's weaker intermolecular attraction between the molecules, right? If there's less of an attraction between molecules, what's going to happen then? There's going to be less surface tension. Is that clear?
So
Understood?
that kind of like explains those thick liquids and not thick liquids. Does it?
But then we are forgetting about temperature, no? We are always include. Now the type of the liquid we are concerned here. We're concerned with what? A liquid whose surface tension changes with temperature. Is that clear?
Oh,
Right?
okay.
I would like to go deep and explain the gradients and everything. It's thermodynamics, but I'm not going to go there about surface entropy and stuff.
Hmm.
You all can read it out because this is not the university, no? So I have to tell you all the other stuff, otherwise we can't cover the syllabus, no? So I'm
Sad.
just going to tell you all what happens to it. Surface tension with temperature. So we'll just accept the graph because it's not something that I can explain in a way that you all can easily understand. But just accept the fact that the surface tension is going to decrease with temperature, right? As Minuka said, it is related to energy as well. So that's because attraction means energy, right? So there's a relationship there as well. But the surface tension is going to what? Decrease with temperature. So this is surface tension and this is temperature. So you can see then that the surface tension is decreasing with temperature. And you can see at a particular temperature known as the critical temperature. Now I remember in the university, we used to study how we got these things, these critical temperatures and everything, the deep science behind it in higher chemistry, right? So if you are going into those places, you can discover. Especially in physical chemistry, we learn about what? Surface tension. So now here you can see at a particular temperature called the critical temperature, what's going to happen? Surface tension becomes equal to 0, right? At critical temperature, surface tension becomes 0. Okay, right. Okay. Now I'm going to come into free mechanical surface energy. Free mechanical surface energy, or you can say free surface energy. That's enough. Free surface energy. This free surface energy is given a symbol gamma, right? So we are going to understand what this free surface energy means. It's a definition. So let's accept the definition. How is it defined? How is it defined? Actually, when you're defining free surface energy, we give one condition. That condition is isothermal conditions. Can someone tell me what is isothermal conditions? Whoever has learned heat, please, I'd like to hear y'all. What is isothermal conditions?
First time hearing, sir. No idea
Yeah,
about it.
iso means same. Thermal. Isothermal means same temperature. Right? So isothermal conditions means what? Same temperature. So
Same
in
temperature.
conditions where the temperature does not change, we are going to define surface free energy, free surface energy. Right? So we say that is the amount of work we have to do to increase the area of a liquid surface by 1 unit. Right? So what is free surface energy? The amount of work that has to be done to increase the surface area of the liquid by what? 1 unit. Okay? But what is the condition? Isothermal conditions. So then we'll define it. The amount of work, very important, the amount of work that has to be done for what? To increase the area of a liquid surface by 1 unit. But what is the condition? Under what condition? Under isothermal conditions. Very important, right? These are the things that are questioned in MCQs that you all have to be aware of. Under isothermal conditions. Okay? Right. So then, now tell me, if the amount of work I have to do to increase the area by 1 unit is gamma, can someone tell me what's the amount of work I have to do to increase the area by an amount A? Gamma is for 1. Therefore, what's the amount of work I have to do to increase the area by an amount A? Gamma A, right? Gamma A, is that clear? Gamma is the amount of work I have to do to increase the area by 1 unit. Then to increase by an amount of A, gamma A is the amount of work I have to do. All right? Is everybody clear with that? Can you all hear me well?
Yes.
Okay.
Yes, clear.
Units, of course, it's up to you all to discover the units, right? Those are very basic things. I'm not trying to do the traditional work there. So now we have a very important proof to make. A very important proof to make. Proof of surface tension being equal to gamma, right? So proof of what? Surface tension being equal to gamma. What is gamma? What is gamma? Free surface energy, no? Remember, free surface
Free
energy.
surface.
So then I'm trying to show that T is equal to gamma, but under what conditions? Under what conditions? Under isothermal conditions. Very important. Under isothermal conditions. Okay. Now let's understand this particular diagram I'm drawing. Just consider a frame, a wireframe, right? Some kind of a wireframe. And just think of a wire that I can move, right, on the wireframe. You can understand, right? There's a wire that I can move on the wireframe. Let's consider this length as P and Q. And then suppose I'm going to have what? A particular membrane, maybe a liquid membrane, right? This has been stretched, so it's there in this area. Okay, there's a particular liquid membrane. So now tell me, right? Now tell me, I'm going to increase the length by X. Let's say I'm going to increase the length by X. What am I doing when I increase the length by X? I am actually increasing the area, right? Do you all agree? If I'm pulling the membrane forward, am I not increasing the area? Yes, I am, right? I'm increasing the area. Now, if you think of this, now just think about the occasion in which you have not increased the area. Just stop there for now and observe. If you observe this, you have to ask this obvious question. Can it be like this in the first place, right?
When we're increasing the area, so does surface tension decrease or something?
Surface tension is not a thing that decreases with external factors like a physical thing that we are doing, right? So like maybe when you're putting some hydrophobic molecules or surfactants or something like that, it will change. But like here, we're not talking about that, Amaya, right?
Okay.
Good question, by the way. We're just putting this, right, forward. Now tell me, if you think about this, the area is increasing, no? The area is increasing. So it will come to a particular position like so. A new position. Now tell me, if you just look at the situation here, right here, they have marked P and Q. Can there be an equilibrium? If everything is smooth and everything, think of the rails as being smooth rails and everything. Can there be an equilibrium?
No. No.
Then what should happen? If I'm supposed to push this forward, I should have an equal and opposite force, right?
Yeah.
Now see, I'm going to apply force forward. That force that I apply forward is what? F dash. And there are surface tension forces occurring backwards along this line, no? As I explained last time, remember. Surface tension forces acting along this line. Okay? They're acting along this line. So there's going to be a resultant of those surface tension forces, which I'm going to mark as F. Can someone tell me what is the value of this F? If I tell the length is capital L, if the length is capital L, can someone tell me what is the value of the force F?
EL maybe? I don't know.
You're saying TL. Surface
Maybe.
tension is the force acting on a unit length. Therefore, the force, total surface tension force is T into L. That's what you felt, right, Amaya?
Kind.
2.
Someone is saying 2. Who's saying 2? TL.
It's me. 2 TL.
Can you justify your answer?
So it's something like elastic, like the one we did back in the beginning. Like spring constant and stuff.
Yeah,
Like,
well, that makes
yeah.
sense, Amaya. Yeah, okay.
It's
Sorry?
acting. No, sir. No, sir. Minute.
Okay, you had the perception of 2, ne? From somewhere you feel
Yeah.
like it's 2. But it's difficult for you to explain, I know, right?
Something to do with that X?
No, they're very different. No, it's about two surfaces up and down. On the front
Oh.
side and beneath, there are two surfaces now. You forgot that, right? So you see, there are two surfaces. When you think about this, I'm going to look from this side. Suppose I'm observing from this side. Then what do I see? What do I see if I'm observing from that side? How are the surface tension forces occurring? If I observe from that side. Then can you see, it's going to be like, if I observe from that side, then I can only see the diameter of the wire. Then the film is like this, right? Then surface tension forces are occurring. Surface tension forces are occurring like that. Can you see? From both sides. From the upper surface as well as what? The lower surface. So surface tension forces are occurring from above and also from below. Is that clear now? So T into L is going to be the surface, the total force that's acting on the upper surface due to surface tension. But on the bottom surface also there's another T into L term. Therefore, the total force acting backwards is what? 2TL. Is that clear now?
So does it change if it wasn't a wire?
Only thing that might change is the dimensions, right? It depends on the object that you're defining. So surface tension is going to be the force per unit length. So depending on the object's dimensions, that other length is going to change. Okay?
Oh,
That's the idea here, right?
okay. Okay.
So F equals 2TL. Now, what is
Okay.
F dash? What is F dash now? The external unbalanced force I'm applying. External unbalanced force. I have to apply. That I apply, right? I have to apply that force. If I'm trying to move it forward, when I am moving it forward, I'm trying to put these words so that you all feel it. When I'm moving the wire forward. Forward. With what? With the film. With the film. Okay? Right. Now listen. Now tell me, if I am pulling this wire along with the film a distance x, what is the work that I'm doing? The force that I have to apply F dash is equal to what? 2TL in the minimum. No? Now remember, I can't apply a force greater than F. Now F dash has to become a tiny bit greater than F, but it cannot be too big. What will happen if F dash is substantially greater than capital F? What's going to happen? It's going to give you kinetic energy in the first place. We are not trying to find that out. We're trying to find out surface energy that's stored. Is that clear? That's our ultimate goal. So the work that we do is going to be effectively stored as what? Surface energy in the film. Is that clear? Right? The work that we do is going to be stored as surface energy in the film. So that's the work I did. Energy has to come from somewhere, right? Understood. Does the film naturally like to increase its length? Or does it like to decrease its length? I mean, the effective area. Does the film like to decrease its area or try to increase its area? What do you think? We
Increase.
learned about it.
Increase.
Increase?
By
No, decrease.
to decrease? Not
Decrease.
able.
Yeah, because we are trying to reduce the potential energy. The number of, you see, we are trying to reduce the potential energy. Now
Hmm.
we are going to store energy, right? We're going to store energy. So we have to do work, right? We have to do work. That's why I'm pulling this forward. When I'm pulling this forward, the work that I do is effectively stored as surface energy in the film. That's it. Right? So the work that I'm doing is what? F dash into x. Always remember, we have to multiply the force in the direction of the displacement. Okay? That's the positive work you're doing. They're clear. F dash into x is the positive amount of work that you are doing. But you should understand F dash is equal to what? If F dash is equal to F plus 0.000001, it's basically equal to F now in our calculations. So we are just trying to negate the kinetic energy component here. So we are finding out whatever the energy that the system gains is due to the work that I'm doing, right? So then work done is equal to F dash into x. What is F dash? 2TL into the displacement x. That is the work that I did when I moved the wire forward. But you understood also, previously I discussed that the free surface energy is defined as what? The amount of work that has to be done to increase the area of a liquid surface by 1 unit under isothermal conditions. Okay? Now understand this. Work done equals what? Gamma A. Energy stored is equal to gamma A. See, now the energy that's stored in the surface film is equal to the work that I did. So then I can make gamma A equal to what? The work that I did. 2TLX. But you see, what is the effective area that increased? What's the effective area that increased? Well,
Yes.
the effective area that increased was
LX.
into 2. Lx into 2. Upper surface and bottom surface. Don't forget that, right? Upper surface is also increasing by Lx. Bottom surface area also increases by Lx. Always you have to picture the three-dimensional thing, right? See from above and below. So you know overall increase in the area is 2Lx, na? That clear now? 2Lx, okay? Equals 2TLx. Now do you see Lx and Lx cancels off. 2 and 2 cancels off. Gamma equals surface tension. Do you all see that? Gamma equals surface tension. Can someone tell me why isothermal conditions are important here? Why?
Why?
Why are isothermal conditions important here in this scenario? Yeah, please, I'd like to hear you all.
So that the tension would stay constant or something?
Surface tension depends on temperature. Very good. You saw that, right?
Yep.
Surface tension depends on temperature. So if the temperature changes, surface tension changes, right? So then if the surface tension changes with the temperature, what will happen? This T is also a variable. Then you have to use calculus. Then you have to get, you have to get the integration of this, right? You have to integrate it because both F and X are variables. I mean, of course, you can change the temperature and at the same time increase what? The distance, right? But then there are two variables. You all have not learned in your level syllabus to use calculus, which is very unfortunate, right? But when you all go into the university, you'll be learning about that. And those math students have already learned about it. Are there any math students? Oh yeah, of course. Amma is there.
I have not learned
But
that yet.
Melissa is a bio student, no?
So,
Yeah, that's the thing. Free surface of a liquid. Shape of the free surface of a liquid. Now, let's understand this simply. I told you about the sphere of influence, right? Now, if you think about a molecule which is here, the interactions are happening like that. Right? And also, if you think about this, there are interactions that also happen with what? Interactions that also happen with the other surface. Now, here I have marked here right now, what I have marked is the interaction of the water molecules with other water molecules, if this is water, right? And you can see, this water molecule is also being attracted to what? The surface molecules. In the wall, think of this as the wall. So the wall has an interaction with the water molecule. So those interactions I can mark like this. Understood? So this is called the sphere of forces or sphere of influence, right? So sphere of influence. Now tell me, if I draw another diagram here, if I mark F, let's say FL as the force that the liquid attracts this particular molecule, right? Think of that. So think of this liquid molecule here, right? And think that the liquid attracts with the force FL. Now, the solid surface here is going to attract overall, it's going to be like that now. Overall, it's three-dimensional. It's going to be like that. But then again, I can mark it separately. I can compartmentalize that into what? Upper overall force, like that, and lower overall force. To always think this is a sphere though. I'm not having the proper dimensions. I'm just trying to point out, right? So then you can see if S is going to be what? The force that the solid surface exerts from one half of the sphere of influence, right? And the other half was Fs. Okay? Right. Now tell me. You see, if you observe this, do you see kind of a resultant force? Like if FL is greater than Fs, what's going to happen? I can draw another diagram. If FL is greater than Fs, you can understand. I can mark the resultant force as what? FL minus Fs. Along this line, I can mark the resultant force FL minus Fs. But you can see that if I construct this sphere of influence, right? Now here, whatever the force there, I subtracted now. So now I have to think only about this Fs acting down, right? Fs acting down. Now we are going to have the picture of this. It's very important. Keep this in your mind because we are going to use this diagram to understand a lot of things. Listen carefully. Just put that into your head. Digest this. Okay, so now tell me, if I have a situation like A, where I'm going to see if, for example, situation 1, for example, if Fs is going to be greater than Fl minus Fs, that means I'm thinking this force Fs is going to be greater than this resultant force Fl minus Fs. Okay, I'm going to think about that scenario. Now Fs is going to be greater than Fl minus Fs. Now tell me, if that is the case, just think of vectors. You all have learned vectors now. So here, Fs is greater than what? So I'm drawing the boundary. Think about the situation. Sorry, this situation where Fs is greater. What's going to happen if Fs is greater than Fl minus Fs? You draw the parallelogram. You know vector rules, right? So let's draw the parallelogram and see. You are going to get a resultant like that. Which means the liquid surface behaves in a fashion like this. Do you understand?
Yeah, sir.
Very interesting, no? Now you see
Sir.
why. Have you all seen these things when you're taking readings from measuring cylinders and stuff,
Yeah, okay.
right? These are the meniscus we're talking about. The meniscus, right? Meniscus. You can see meniscus there. And now tell me. Now we can think of another situation. What if we have another situation where Fs is equal to what? Fl minus Fs. What's going to happen then? You all can guess, no? Already? What's going to happen then? This Fs force is there. Now Fl minus Fs is also equal to what? Fs.
Fs.
Then can you understand the resultant is gonna work like this? Then how's the liquid surface going to be there? Like that. Understood? Okay. Now the situation. 90 degrees. Now the situation. So it's a flat meniscus. Now tell me. If in case, so we're going to see situation 2, then situation 3. Situation 3, if Fs is less than Fl minus Fs, what's going to happen? Now what do we have? What kind of situation do we have now? You see, if I think of this, now I can mark, Fs like that down. And of course, you can see now this Fs is greater. So sorry, so I have to make it longer. Now Fs is larger than what? Fl minus Fs. Is that the case or other way around? Other way around, no? Other way around. Actually, Fs is smaller than Fl minus Fs. That means if the cohesive forces are greater than what? The adducive forces, do you understand? Right? Now, in this situation, we looked at what? Where the adhesive forces are stronger than the cohesive forces. That's why Fs is greater than Fl minus Fs. Fl, besides the extent of what? The cohesive forces. So if the adhesive forces are substantial in a situation, then of course you can see the meniscus turns that way. It's touching the solid barrier, right? Of course, you can go into the chemistry and see why it happens. You can see the OH groups in the silicon chemistry of what? Glass, right? So go into it and see. But I'm not going to go into the chemistry of it. That's chemistry, so go into chemistry and see. Now, Fs and Fl minus Fs. Now, if you construct the parallelogram, you are going to see what? A resultant like that. Now, what do you see? Now, the construction of that would be something like this. Here, you're going to have the resultant. It's pentacule. Is that clear now? Okay. Did you all hear me while I was teaching?
Yes, sir.
Okay. Now we're going to talk about the angle of contact. What is the meaning of the angle of contact? That's called the contact angle or the angle of contact. We'll understand that a bit. So I'll use another picture, another page. Angle of contact. Now tell me. Now you see, if I have a particular liquid surface like that, and if the adhesive forces are prominent, right, then you can see that the liquid is embracing the flow, right? Okay, it's embracing the flow. It's attached, no? Adhering. Now, I'm going to draw a tangent to the liquid surface at the point of contact of the liquid with the solid surface. So this is where the liquid is in contact with the solid surface. Of course, there are other locations I was in contact, but I'm looking at this particular point. Right? Then I'm going to what? Draw a tangent like that. Tangent drawn to the surface of the liquid, right? So this is the tangent drawn to the surface of the liquid. Okay, so what I'm going to do is I'm going to make my way swimming from what? Bottom surface and touching what? The tangent through the liquid. So here you can see this is the liquid, right? So this is the liquid. So I am going to come from what? The bottom surface, right? And I'm just going to swim through the liquid and touch the tangent. This angle that I cover when I go from here to here is what? The contact angle. This is the contact angle. Understood? The contact angle. So then I can say the angle made by the tangent, at the point of contact of the liquid surface with the solid surface. Inside the liquid. Here's the definition of what? The contact angle. Of course, this is like having some water, right? On a glass slide or something. But now if you think of mercury, mercury has very high cohesiveness. So mercury is going to be pronouncing itself like this. Right? Something like this. Don't know if they can recognize this kind of a diagram. Right. So here you can see I can mark the tangent and draw the tangent. Then I'm going to swim from this surface and end up at the tangent. Then I can recognize what? The contact angle. It's very large, no? It's greater than 90. So this is the tangent to the liquid surface. Okay. Understood?
So it's kind of like this water drops on like an oily surface, you could say.
Yeah. Then you can see the same phenomenon. No? So it all depends on the surface chemistries of what? The two surfaces. I mean, the surface and the water, right? Or the liquid. Liquid and the surface, depending on how they interact with each other, depending on which forces are more stronger, right? Then they're going to either be in this shape or in this shape, right? Okay. Right, so, but in questions for convenience, they give you situations like this, where the contact angle is like 0. Like that. What's the contact angle here? It's 0, right? So the contact angle here is 0. A situation like this, contact angle is 90. Okay? Right. Can someone tell me, if I put soap to a water surface, is that going to decrease the surface tension or increase the surface tension?
Soap for the water surface.
Yeah. If I put some soap
It's
to water,
decreasing the surface tension.
why?
Because the soap molecules are disrupting the cohesive forces, no, that is between the water molecules at the surface. Like they are just the water molecules are normally pulling each other tightly. So the soap molecules are getting in between, and then it's like weakening it, so the tension decreases.
Very good. You are trying to say that they are throwing the water molecules apart. Is that your idea?
Yeah.
Yeah. So they're trying to say that they're trying to move things apart. Actually, if you go deeper, actually we learned about this.
Could be
Stretching
something
the
related.
surface tension.
I'm sorry.
So could it be something related like polar, non-polar or something?
You're talking about actually, I think Rita has done the phospholipids, no? The polar
Yeah.
head and what? The tails.
Yeah, the tails.
So then they are, okay, now if I tell you about the soap, there's a hydrophilic component and a hydrophobic component, right?
Yeah, water loving and water avoiding.
Water loving and
Parts.
water avoiding. So what would the soap do? like a soap or a detergent do? It will start interacting with what? Like if the head will start interacting with what? The water molecules, right? But because this hydrophilic means water loving, right? The water loving groups will interact with the water molecules. It's like this now. If I draw it, so now normally water molecules can interact with each other na, like that. They can interact with each other, right? But what happens when like, if you think about other surrounding water molecules, they can interact with each other like that. But the moment I put a detergent molecule, what happens is, for example, it'll spread itself like this, right? So the hydrophilic head is called the hydrophilic head. Hydrophilic head. Right? It loves water. Hydrophobic tails, it hates water, right? Hydrophobia. Phobia means phobia, right? So hydrophobic tails. So these are what? Non-polar groups, fatty acids, right? So those are avoiding water because of the chemistry, right? But the polar heads, they have a chemistry that allows to interact with what? Water. So now they're interacting with water, but the tails are repelling water, right? So then this is going to actually, what is it going to do? It's going to eventually reduce the surface tension. Is that clear? Understood?
Yeah, sir, because they're decreasing intermolecular forces in a way.
In the sense, yeah, you're not allowing them to have those forces,
Hmm.
right? So adding soap decreases surface tension, right? Very important point for MCQs. Okay. So that's a very nice lesson, no? Surface tension, practical, loving lesson, right?
So could we try to explain it this way?
Yeah, please do.
Since the water has a negative charge and let's say somehow the water dissociated into H plus ions and soap is basic, right?
Thing,
Maybe
Mirka, is I mean, I like your argument. It's a very good one, but the thing, Mirka, is the problem is water dissociates very less. It's like 10 to the minus 7 mole per decimeter cube, the H plus concentrations and the OH minus concentrations, right? We've done the pH equilibrium, no? I mean, the equilibrium of water KW is H plus into OH minus, but there the amount of water that is broken down is negligibly small compared to the water that is there unbroken. So most of the water molecules are, anyway having tremendous number of hydrogen bonds. They're clear,
yes, sir.
right? A very good question, by the way. So because